Hi guys. Hi guys, in this video I'm going to do some problems from this chapter electrostatics. So my assumptions here is like you already familiar with Coulomb's law and also Newton's second law. So please, if you don't know these two laws, you can go and read about these two laws so that you can understand what's going on in this video. So in this video, we're just going to solve some tricks problem from electrostatics, but using these two laws, Coulomb's law and Newton's second law. So let's get started. We got this problem here. It's example one that I'm going to do with you. So it says that two identical 0.017 kg spheres are attached to and non-conducting threads affixed to the ceiling. So for the first statement, that means we're going to have something like this. This is the ceiling, and then here you have the first mass. Here you have a second mass. Both of them are attached to these threads. So and attached to the ceiling. So initially the spheres touch each other. So initially let's call this A here, and then let's call this B here. So initially the spheres touch each other, meaning that here they touch each other. So for B, we're going to see what's happening with the spheres. So it says, but then an equal amount of charge is put on each. So therefore here we have Q1, here we have Q2. So that statement, an equal amount is put on each. So therefore Q1 is equals to what? To Q2. Okay, so if each thread is 120 millimeter long, so that means this distance from here, this distance from here to here, it's L. So L is equals to, let's call this distance L. So L is equals to 120 millimeter long, and the spheres come to rest at the separation distance of 93 millimeter. So that's B. B is like this. Since each sphere has an equal amount of charge, and they're both positively charged or negatively charged, so therefore they're going to repel, because we know from Coulomb's law that the two charges that have the same sign repel, but the two charges that they have an opposite sign attract each other. So here we know that these spheres is either can be negative, both of them, or they can be positive. So they can be negative or they can be positive in order to repel. So after repelling, they told us that the separation distance between them, that distance is equals to 93 millimeter. It's 93 millimeter. This is the distance of separation between them. So we don't know about the angles, we just know about the L and the separation distance. Okay, so after that, now we'll ask this question. What is the electrical charge on each sphere? So now we have to calculate what is the electrical charge on each sphere that will cause this sphere to separate this distance after they touched each other. So okay, so now here we're going to start with the Newton's law. As I told you earlier, we're going to do Newton's law and Coulomb's law at the same time. So we're going to start with Newton's law. Let's draw a free body diagram here for one sphere at this position B, for this one here. Let's draw a free body diagram for that sphere. Let's choose this sphere 1 here and draw a free body diagram for sphere 1. So let's draw a what? A free body diagram of that sphere. So the free body diagram, you can see that from here, this sphere here, this one here, the first thing that I see is that the sphere is stationary, as they told me that the spheres are at rest after separation. Okay, so since I know that this is it's at rest, then one force is exerted downwards, because this sphere got mass, right? So we know that each object that has a mass on Earth is going to experience a weight. So therefore, this sphere has a weight here. A weight is going down. So to do that, I'm going to start with weight. So weight is going this way. It starts here, going down. This is weight, right? I'm going to call this W. And then after that, what makes the sphere to be in this position? Remember that initially the sphere was here. initially the sphere was here. So what made the sphere to move from here to there is a force of what is this? Force of repulsion from the other sphere. So the force of repulsion, as you can see, is going this way. So that's therefore the force of repulsion is from here going this way, because this sphere are equally charged. So let's call that Fc is a force of repulsion, but it's a Coulomb's force of repulsion due to the another sphere. Okay, so now what's a resultant? A resultant is this one here, right? Is this from here to there? This is the resultant. So that's the resultant. Here we have a weight. Here let's write this W outside here, so we don't get confused. W is here, and then here we have an angle theta, right? So this it's a resultant of these two forces. So let's just call that capital letter R. But we can see we can use the same sketch to make another argument of let's say of a displacement, because we are told that this displacement here is this L. So this is L. Let me write that in a proper manner. This is it's L, and then this let's call this H. We are not given that. And then this distance here, you can tell me what's that. You can tell me by looking at the sketch. So this distance here is gonna be half D. So this distance is a half D, while the distance from here to here it's D. So therefore the distance from here, from half of this to there, it's a half D. So therefore if we did this is going to be our first step. So what's our question again is to calculate the electrical charge on each sphere. What's the electrical charge on this sphere? What's the electrical on that sphere? So since we know that these two things got the same charge, so we have to look here in these two diagrams, which one can give us the electrical charge. We have this diagram here, this diagram. So that diagram, from this diagram we can see that we have a Fc. So we know that Fc can give us a charge, because Fc from Coulomb's law, Fc is equals to K, which is a Coulomb's constant, Q1 Q2 divided by R squared, which R squared is the distance between the two charges. So therefore we can use this argument that from this sketch we can get Q. All right, so from this sketch here we have this is theta here, so these two thetas are equal. What we can get from that sketch? Okay, we are going to see what we are going to get from that sketch. So let's move on. All right, so let me copy this down so that we can use this information to the next page. Let me just copy this, the information, initial information that we're given. So remember that we got this. Let me put this here. We got this, and then also initially we're given, let's write all of the things that we're given. We're given that the distance between these two churches, it's 0.093. I converted that to meter. Don't be surprised. And mass in each sphere is 0.017 kg, right? So, and again the length, the L, is equals to 0.12 meter long, right? And then the K, we know that K from Coulomb's law, it's 9 times 10 to the power 9 Newton meter squared per Coulomb squared, right? Okay, so we want Q. We don't know what's Q. So okay, we're going to use these two sketches to find Q. So let's use the first one, this first one here. We know that from this sketch, what's tan theta? Tan theta is equals to, let's look at this, tan theta, remember that's opposite over adjacent. So opposite side, our opposite side is W, our adjacent side is FC. Okay, so we can take again tan theta from this sketch. So tan theta from the other sketch, tan theta from this sketch here, it's equals to H over 1 over 2, what is this, D. All right, so if you got these two, now we can calculate what's h, because from this sketch we know that we have L, we have a D, so we can calculate what's h. So from the sketch, you know, by using a theorem of Pythagoras, h squared is equals to L squared minus 1 over 2D squared, right? So we can say that h is equals to the square root of L squared minus 1 over 4D squared, right? All right, so that's our h. And then here we got tan theta, also there. Okay, so now we can equate these two, because now let's rewrite this tan theta by substituting h. Tan theta here, let's substitute what's h. What you got? It's a square root of L squared minus 1 over 4 D squared all over half D. So remember, the reason of doing this, it's like we are not given what's h. So we want to substitute h with what we are given, which in this case we're given the L and the D. So we can use these two to find h using a theorem of Pythagoras. Okay, so now we have these two things here. We have tan theta here, we have tan theta here. So let's look. We know what's weight, right? From Newton, we know that weight is equals to the Fg, right? So which Fg is equals to mg, which is a mass multiplied by the gravitational acceleration. So we can use that argument to say that, okay, so since we know here what's weight, we know what's electrostatic force. From electrostatic force, remember that previously we said that Fc is going to be what's this? It's going to be K Q1 Q2 R squared. So the distance between the two spheres, we know what's that. The Q1 and Q2, we know that these are the same, so therefore this is one unknown. We don't know what's that. Is this one here? Is that one? So we don't know what's that. So K we know. Let's go to another tan theta. L we know what's L. D we know what's D. So therefore, if we can equate these two tan theta, we can calculate what's Q, right? Because here we only have one unknown, which is Q. There we don't have an unknown. Then we can equate these two equations, and we're going to get our Q. So okay, so let's copy this again and then do that on the next page. All right. Okay, so what you have to do now is just to equate these two equations, this one here and this one here, because both of them are equal to tan theta. So okay, so I'm going to do this quickly. We know that what's weight, right? Weight is just mg over Fc. We know that Fc is this one here, is K Q1 Q2 divided by R squared is equals to the square root of L squared minus 1 over 4 D squared divided by half D. So now I'm going to ask you to pause this video and try to simplify this equation. Just try to simplify and make Q as the subject of the formula. Remember that Q1 is equals to Q2. So therefore, if Q1 is multiplied by Q2, that's the same as Q squared, right? So I'm going to ask you to pause this video and do a rearrangement of this, making the Q the subject of the formula. Okay, so I guess that you got this. You got that Q squared is equals to D cube mg divided by 2k the square root of L squared minus D squared over 4. If you did your math correct, this is what you are supposed to get. Okay, so let's just do a substitution now, because we know what's D, we know what's M, we know what's G, we know what's K, we know what's L. So let's just do a substitution. So we're going to say, D is the same as 0.093, right? And then we cube that, and then we know what's M. M is 0.0 17, and then G is 9.8. G it's 9.8. Then after that you divide this by so you have 2k, 2, so what's k? K is 9 times 10 to the power 9, right? And then you have a square root of what's L. So L is the same as 0.12. You square that, and then minus what's D. D you are given your D is the same as 0.093, and then you square that. You divide it by 0.93. I forgot 3. You square that, you divide by 4. So therefore you are going to get that Q squared is equals to this is going to give you 6.729 times 10 to the power minus 14, right? C squared, right? So that's a column squared. So now you want a charge which charge is calculated in column. So therefore Q is equals to, you square this, you're going to put a square root here like this. You're going to put a square root both sides so that a square root can cancel a square. So you are going to get 2.6 times 10 to the power minus 7c. So don't forget, because as you square this, that can be positive or can be negative. So as I told you when we started, that the charge can be positive or can be negative. So if it's positive, both of them are positive, they repel each other. If both of them are negative, also they repel each other, which gives the same answer. Okay, so this is the end of our video. Thanks for watching. See you next time. Don't forget to subscribe. Okay, thank you.